So far, we have seen the building blocks of an RX chain, which takes an RF input and finally generates a digital output. We have also seen building blocks of transmitter chain, takes digital input, generates RF output, and in a transceiver system, this transmitter chain and receiver chain both are sharing an antenna with the help of a duplexer. And in addition to the receive chain and transmit chain, we have been always assuming that there is a local oscillator available which can generate the required periodic signal for the frequency up conversion and frequency down conversion. This is the local oscillator. Now we are going to focus on this local oscillator. We will try to see how we can generate the periodic signal, what kind of circuitry is involved, and also we will try to understand what are the specifications which decide the performance of a good local oscillator. So this oscillator is a self-driven system in the sense that it doesn't require any input signal. It can directly generate a periodic signal as an output just by consuming some power from the DC source. It generates periodic signal. When we talk about oscillator, we are mainly interested in the accuracy of this periodicity. So we want the oscillator to have very accurate frequency or time period. So when we talk about oscillators, mainly we talk about the frequency and to even understand how good is the oscillator, we have to specify the purity of this periodic signal. So that is also called as spectral purity. In addition to having this frequency as one of the specifications, we also want the oscillator to generate high amplitude because the oscillator is going to drive various stages in the transmit and receive chain. So high amplitude signal is going to simplify the overall design, and later on we will see that if the amplitude is high, then overall noise performance of such oscillators are also much better. Frequency and amplitude. Since it is a self-driven system, we need to first understand how we can design a circuit which can generate signal on its own. And to understand such self-driven system, we can take some example from our day-to-day life, where we have these two inclined surface which are connected in a smooth manner. So if we place a ball here and we leave this ball, then from our experience, we can easily see that this ball is going to roll down this inclined plane, and while doing so, it is going to lose potential energy and gain kinetic energy. So at this point, it is going to have the maximum speed. And again, it is going to climb up on the other inclined plane, where at the highest point, it is going to have again maximum potential energy and zero kinetic energy. If this ball is starting with a height h, under this scenario, it has maximum potential energy. Then this ball rolls down. Here it has maximum kinetic energy. And using this kinetic energy again, there is an exchange of energy. Finally, it is completely converted into potential energy. And if we leave this system, assuming there is no friction in place, then we know that this ball is going to roll up, down, and so on forever. So if I have to track the position of this ball in this x direction with time, this is x time. So now we can see that we are starting from some position on the negative side of the x, but as time progresses, it is becoming 0, then becoming maximum on the other side, again 0, and so on. And this is going to continue forever. So this looks like a system which is self-driven, doesn't require any external input. You start with some initially stored energy, and as time progresses, there is a continuous exchange of this energy between the two forms, which is again happening at a very specific rate. So the rate at which this exchange of energy happens completely depends on physical properties which are present in the system. So for example, here, the mass of this ball, in addition to that, what is the gravitational acceleration, g. So these two factors are going to decide at what rate this exchange of energy is going to take place. So we can see that this is an example of self-driven system. There is a continuous exchange of Ke and Pe, and the rate of exchange depends on the physical properties. Here the mg. So the height with which we start initially is only going to decide what will be this amplitude of x, what will be the maximum swing. whereas the rate is always going to be decided by the mass and the g. So that is not going to change with respect to the initial condition of the system. Now here we can look at one more detail which we observe in real life. So in reality, what happens as the time progresses, this ball will not reach to the peak because of the friction which is present. So part of the energy is going to be lost over time. And finally, it is going to come at rest in this stable position. So if we plot the case when friction is present, we will see that this x versus time is going to look different. We will see that there is going to be an exponentially decaying envelope if we plot x versus time, and it may look like this. So on. So we will find that period t is same as period which we had in the case when there was no friction. We're talking about exponentially decaying envelope due to loss, in our case, friction in the system. But the period is still going to be same. It is not going to change because of the loss. It will only be dependent on what is the physical properties, in our case, the M and G present in the system. So in reality, such systems are not able to sustain the oscillations. Okay, so these oscillations are going to die down because of practical laws. But at least this example gives us an idea that it is possible to create a self-driven system where we have two forms of energy and they are coupled in such a way that there is a continuous exchange between the two forms. And this rate of exchange only depends on the physical properties and doesn't depend on the initial condition. So by taking an inspiration from this example, we can also try to design an electrical oscillator where we have the energies which are coupled through some electrical circuit so that there can be a continuous exchange resulting in a periodic output. We have to design an electrical system where two forms of energy can be stored and coupled to allow change of energy. So we need these two forms of energy. Then we will try to find out how to couple them. So in electrical domain, we already know that we can store the energy in electric field using capacitor, and we can also store energy in the form of magnetic field inside inductor. This is capacitor stores electrical energy and an inductor, if the current is flowing through it, then it stores magnetic energy. So if we can couple these two elements, then it is possible that we can obtain a system where these two energy can be exchanged back and forth, resulting in a oscillatory output. The simplest way to couple these two elements is just connect in this manner such that the electrical energy stored, which appears as voltage, case of the capacitor, can drive current in the inductor, which results in magnetic energy to be stored inside the inductor. So just by shorting the two elements in this manner, we can ensure that they get coupled and there is a way for exchange of energy between the electric and magnetic form. So in this simple LC circuit, we can try to find out how the voltage and current evolves over time. So let's say this is the voltage VC and this is the current IL. So for this simple circuit, we can write the relationship between VC and IL. We know that VC is going to be equal to L di by dt from the inductor relationship. Similarly, we can say that the current IL, which is also the current coming out of this capacitor, to be equal to minus C dV by dt. By using these two equations, we can see that this Vc of t is equal to minus Lc double derivative of Vc itself, or Lc double derivative of Vc plus Vc is equal to 0. This is a linear homogeneous differential equation, and we all know that this is of the form of the simple harmonic motion. So one way to find the solution for this equation is we can write its characteristic equation as Lc s square plus 1 equal to 0. And from here we can find the roots of this equation. And using these roots, we can find the solution for this differential equation. So it implies the roots are going to be equal to plus minus j by root over Lc. Let's call this 1 by root over Lc as omega naught. These are the roots of this characteristic equation. We can see that the roots are purely imaginary. Now using these roots, we can find the solution for Vc. So it implies Vc of t is going to be of some form a to the power j omega naught t plus b e to the power minus j omega naught t. Okay. And using the initial conditions, we can find what is going to be the value for this constant. And accordingly, we are going to find the expression for this Vc of t to know how Vc evolves with time. Now, in our case, since we know that Vc is going to be purely real, so it means these two coefficients have to be complex conjugate of each other. For real Vc of t, A should be equal to the complex conjugate of B. Implies Vc of t is going to be, if we expand, we're going to get Vc of t of this form, A naught of cos of omega t plus some phase phi, omega naught t plus this phi. So now we can see that this voltage is going to be a cosine function. So this cosine function is going to repeat forever with an angular frequency of omega naught. And similarly, we can find the expression for IL of t. So that is also going to be a sinusoidal function with some amplitude and phase. So we can see that Vc of t and IL of t are sinusoidal function of time with frequency f naught is equal to 1 by 2 pi root over LC. So this frequency of oscillation is only dependent on the physical values of this inductor and capacitor. And based on the initial condition, we can figure out what will be this amplitude and the phase for voltage and current. Initial condition, decide amplitude and phase. Let us take a case where this capacitor is initially charged to some voltage V naught. Say the initial condition at t equal to 0, Vc of t is equal to V naught. IL of t is equal to 0. Implies your Vc of t, which we have written a general expression as A naught cos omega naught t plus phi. Since IL is going to be sine function and its initial value is 0, so we will find that the phi is going to be 0. And then we can easily see that if Vc is equal to V naught, then this A naught should be equal to V naught. We can say that this Vc of t is equal to V naught cos omega naught t, where omega naught is equal to 1 by root over LC. So in this simple LC circuit, to add the stimulus, we can also think of connecting a current source, and with the help of current source we can add some energy to the system without changing the characteristic equation. So we can redraw the circuit. Source, and we can take this as the output. So if the current is 0 and these capacitors and inductors are not initially charged, then this V0 is going to be 0. So if you want to excite the system, that can be achieved by applying an impulse from this current, and this impulse current is going to charge the capacitor. So if the I in of t is, let's say, unit impulse current, in such a scenario, the output voltage at equal to 0 plus is going to be equal to, so this impulse current is going to flow in this parallel combination, and because of sudden change in the current, entire current is going to flow only through the capacitor. This inductor will act like an open circuit. So the amount of charge fed by this current source is going to completely appear in this capacitor, and this capacitor voltage is going to be equal to 1 by C. So now if we look at this voltage over time, we will get this cos function like this, with the amplitude to be equal to 1 by C. And this period t is going to be equal to 2 pi by omega naught. Okay. Omega naught is equal to 1 by root over LC. So this is the same situation which we had just discussed earlier. Now in this case, we can also talk about the transfer function from this input to the output. So to find the transfer function, we can write this voltage and current in the Laplace domain. So this V naught of S is going to be equal to I in of S into this parallel impedance of L and C, which is equal to SL into 1 by SC divided by SL plus 1 by SC. So it implies the transfer function V naught by I in is going to be equal to SL divided by 1 plus S square LC. So this is another way of looking at the same circuit, but now we have got a stimulus and an output. So now we are able to talk about this transfer function. So we can see in this transfer function, the poles are completely imaginary. So because of this purely imaginary poles, we know that the impulse response is going to result in sinusoidal output with constant envelope. So here poles are at plus minus J by root over LC. Now this looks like such a simple circuit can be used to design an oscillator. We just need to add some initial condition. But in reality, what happens, there is always going to be loss in the system, as we have seen in the case of ball rolling down the slope. There also some friction will always be there, which will result in a damped oscillation. Similarly, here also, these capacitors and inductors are going to have some loss, and there will be also loss in this interconnection. So as a result of which, this V0, if we are going to look in a practical system, will not have this constant envelope. Over time, the amplitude is going to decay. So we can model the loss in the system with an equivalent parallel resistor, and we will try to see how the output voltage evolves with time. See tank in the presence of loss. We will be having this capacitor, inductor, along with that parallel resistor to model the loss in the system. This is our output V0. Again, let us assume that we are using a current source to excite the system. So this is C, L, and this R. We are interested in this V0 of t. And again, we will assume that this In is an impulse current, which is going to charge this capacitor to an initial voltage of 1 by C. So we can find the output for an impulse current by writing the transfer function V0 of S divided by In of S is going to be equal to, in this case, it's parallel combination of LCR. So this will be 1 by R plus L plus SC, which is equal to SL divided by S square LC plus SL by R plus 1. So this is a standard second order system characteristic equation. Now we can plot the output voltage when an impulse current has been applied, just like the earlier scenario without any R. So this is the kind of output voltage we are going to get when there is no resistance, there is no loss. No loss the tank. When R is present, we'll find that poles of the system are going to have a negative real part, and this negative real part is going to result in a exponentially decaying envelope. So initially it is going to start from the same value. Time progresses, it is going to show a reduced amplitude. Like this. The presence of R modeling tank loss. So we can easily see that as time progresses, this output voltage is going to become 0, and we won't be having a sustained oscillation. So if you are trying to design an oscillator just with the help of an inductor and a capacitor, you will find that always there is going to be some loss in the system, resulting in this kind of decaying output amplitude if we start with some initial condition, and finally it is going to become 0. So a practical LC tank has loss resulting in decaying impulse response. So let us relook at this circuit. So it has this capacitor, inductor, and then this resistor. Here we are taking the output V0 of t. So we can see that within this inductor and capacitor loop, there is an exchange of energy, whereas part of this energy is always leaking towards this resistance. Since we have some output voltage, so this V0 by R current is going to flow through this R. So as a result of it, slowly the stored energy is going to dissipate through this resistance. So here energy exchange happens between L and C, but we have this current IR which has to flow, resulting in the loss. So over time, the stored energy in the system is going to become 0. Current through R dissipates energy over time. So looking at the circuit, if we want to have a sustained oscillation here, while making sure this IR doesn't come from this LC parallel combination, because if this current comes from here, then slowly the stored energy in this tank is going to become 0 over time. What we can do is, we can sense this voltage V0 and try to supply this current from other source so that the energy stored in this LC tank doesn't decay over time. So what we can do is find a way to sense this voltage V0, and based on this voltage we will supply this IR externally. And to do that we need some active circuit. The job of this active circuit is supplies IR to the resistor so that energy stored in LC tank stays constant. Now we can see that if the equal amount of current comes from this side, then current here will become 0. Okay, the current which is coming from this LC tank towards the resistor. And if we can design such an active circuit, then we can say that once the LC tank has been stimulated with some initial energy, then it is going to maintain this energy forever, and we are going to get a sustained oscillatory output as long as this active circuit is exactly compensating the current which is flowing in the resistor. Okay. Now, if we look at this active circuit, the way we have drawn, it's a two-terminal device. And for this two-terminal device, we can then talk about its equivalent impedance. So it is providing a current IR while the voltage is V0. So if we look at this Zin, it is equal to V0 divided by minus IR. Okay, because this current is coming out, and we already know that V0 by IR is nothing but this resistance R. So it means this input impedance Zin is equal to minus R. Okay, so it implies we need a negative resistance of value minus R to compensate loss due to R in the lossy tank. So the complete circuit for this LC tank based oscillator now has capacitor, inductor, R, which is modeling the loss in the tank, and a negative R. So this is the equivalent circuit of LC tank based oscillator. We need to just figure out how to obtain this negative resistance, and then we can connect this negative resistance in parallel to this LC tank.